Hello everyone. In this lecture, I shall discuss the Taylor and Maclaurin series expansion for single variable functions. Now, prior to that, I should continue the remaining part of lecture 1, the maxima minima. So, recalling the maxima minima under the first derivative test, if f dash x changes sign from positive to negative as x increases through x0, then fx attains maxima at x0, right? Likewise, if f dash x, so in this context, in view of the second derivative, right, here f dash x itself is a decreasing function, right, for which f double dash x is negative, right. For decreasing function, we have derivative of fx is negative. Now f dash x being decreasing, so f double dash x is negative. So consequently, for second derivative test, we have f dash x0 is equal to 0. This is for stationary point at x0, and at that stationary point the second derivative is negative. This is for your maxima. This is for your maxima. And similarly, for your minima, f dash x changes sign from negative to positive, which is same thing to say that f dash x itself is an increasing function. Means first derivative of f dash x is positive at the point x0, right? So f double dash x0 is positive here. So consequently, in view of the second derivative, we have for minima fx is equal to 0 implies x is equal to x0 is a stationary point, and at that stationary point the second derivative is positive. So this is for your minima. Now there are certain cases where f double dash x is 0, right? Means f dash x0 is 0 for stationary point, but instead of f double dash x0 negative and or positive, it is equal to 0. In that case, it leads to a point of inflection subject to the condition f triple dash x0 is not equal to 0. If we want to understand it diagrammatically, we can see the following diagram. So before that, I should introduce myself. I am Dr. Sushant Kumar Paikray, currently working as a professor in the Department of Mathematics, Bir Surendra Sai University of Technology, Odisha, Burla, Sambalpur. So let me to make you understand via the diagram. Also, you can refer to my previous lecture 1. As I have told you earlier, for maxima, here f dash x is positive, and f dash x is positive in the left neighborhood, and at x0 it remain constant. Now towards the right neighborhood, f dash x is again decreases, right? So it increases in the left neighborhood, then suddenly after x0 it start decreasing. So here x0 is a point of maxima here. x0 is a point of maxima here. So in view of this, we have f dash x0 is equal to 0 and f double dash x0 is here negative. This leads to your maxima. Of course, the function here is a concave function here. Now similarly, for minima, what will happen? For minima, the function decreases in the left neighborhood. At x0, suddenly at x0 it again starts increasing, right? Means f dash x is increasing in the left neighborhood. At x0 it again starts increasing. So here f dash x is again negative. Means here in the left neighborhood f dash x is in the left neighborhood, here f dash x is increasing, f dash x is decreasing here, and suddenly at x0 it again starts increasing. It starts increasing, right? So at this point it attains here minima. So here f dash x0 is equal to 0 and f double dash x0 is your positive. This is for your minima. Now for the point of inflection, what will happen here? For the point of inflection, you see the curve crosses the tangent, right? The curve crosses the tangent line here. You see here the curve crosses the tangent line, means here the function increases, here the function increases, here the function increases, right? And here also the function increases here. Now here you see the tangent line, the curve lies below the tangent line. Here you see the curve lies above the tangent line, and here the curve crosses the tangent line at x0, right? In this case, in point of inflection, we have here f dash x0 is equal to 0, f double dash x0 is equal to 0, but f triple dash x0 is not equal to 0, right? So this is the background of maxima minima in view of the first derivative as well as the second derivative. To summarize, let me to write the working rule for maxima minima in view of the second derivative. So coming to the working rule for maxima and minima using second derivative test, right? So here consider the function y is equal to fx. Now at step 1, what you will do? You find the first derivative and equate it to 0, and if you simplify it, it will give you the value of x as x0, x1, x2, like this, right? So these are called the stationary points. Right? These are called the stationary points. Now in the second step, what we will do? We find the second derivative, right? And at each stationary point, say at x0, say, right, we find the second derivative. If it is negative, right, then it leads to maxima. And if the second derivative is positive, then it leads to your minima. Likewise, we go for the test at other stationary point, say at x1, right? We test it. If the second derivative here is negative, means it leads to your maxima at the stationary point x1. If it is positive, it is minima at the stationary point x1. Similarly, at every stationary points we go for the test, and there are some situation arises here. I can say that the special case, in special case what we will see, f dash x is already 0 earlier, and we see here f double dash x at say at x0, say f double dash x0 is here 0, but f triple dash x at x0 is not equal to 0, then x0 is a point of inflection. That means neither maxima nor minima at x0, right, in the special case. Now if at x0 we get it, first derivative 0, second derivative 0, but the third derivative is not equal to 0, then it is a case of the point of inflection. So this is the working rule. So based on this working rule, we can evaluate some examples here. Now coming to an important example, you are given a function fx is equal to x minus 2 whole cube into x minus 3 whole square, right? We have to find the value of x for which this function is either max or min, right? Also find the point of inflection if any. Moreover, find the extreme values. So now consider the function y is equal to fx is equal to your x minus 2 whole cube into x minus 3 whole square, right? Now your first derivative test, you find the first derivative. We have f dash x is equal to your product formula, so derivative of first 3 into x minus 2 whole square and x minus 3 whole square remain silent, plus derivative of the second is 2 into x minus 3 and first one is remain silent, x minus 2 whole cube. So if I take common x minus 2 whole square into x minus 3, x minus 2 whole square into x minus 3, it will give you 5x minus 13, okay, 5x minus 13. So it is your f dash x. For stationary point f dash x is equal to 0. So this implies if you solve it, this equal to 0. So x is equal to your 2, x is equal to your 3 and x is equal to your 13 by 5. So these are the stationary points. We are getting 3 stationary points. Now at individual stationary points we see the functional value. Now prior to that, what is my f double dash x? Next, here f double dash x, right, we differentiate it again. So it is the product of 3 functions, right? So derivative of first twice x minus 2 and here second and third remain silent. Now plus first silent, derivative of second is simply 1 and third silent 5x minus 13, plus first remain silent, second remain silent, derivative of the third one is here 5. If you simplify it, it will give you x minus 2 can be taken common throughout. So this will give you x minus 2 into x minus 3 into, just a minute, it will give you x minus 2 into 20x square minus 104x plus 134. You can simplify it to see this, right? Now let us test at x is equal to 2. What is the nature of the function? At x is equal to 2, at individual stationary point we go for the test. At x is equal to 2, here f dash x is equal to 0. Here you see 2 is a factor, x is equal to 2 is a factor. However, so here f dash 2 is 0, f double dash 2 is 0. So here we have to see what will happens to f triple dash 2 at x is equal to 2. F triple dash 2 we have to see it. So if you find this say third derivative and check it, and it must be not equal to 0, you should check it, okay, you should check it, it should be not equal to 0. So consequently, so therefore f dash 2 is equal to 0, f double dash 2 is equal to 0, but f triple dash 2 is not equal to 0. So this implies x is equal to 2 is a point of inflection of fx, right? So this is a point of inflection of fx. X is equal to 2 is a point of inflection of fx. Now similarly we should go for the test at x is equal to 3. At x is equal to 3, what will happens to f double dash x at x is equal to 3? If you substitute x is equal to 3 here, it will give you 2, means it is positive. Since it is positive, it leads to your minima. Therefore, thus fx attains minimum at x is equal to 3, and minimum value and f minima is f of f of 3, if you substitute 3 here in the given problem here, f of 3, and this will here 0 here, right? F of 3 is 0, right? Likewise, at the point 13 by 5 we will see the nature of the function. At x is equal to 13 by 5, what will happen to f double dash x at x is equal to 13 by 5? If you simplify it, it is minus 18 by 25, which is negative, means it leads to a maxima. Thus fx attains maxima at x is equal to 13 by 5, and the maximum value and f max is equal to here f of 13 by 5. If you substitute 13 by 5 here, then you will get it 108 by 3125. So this is the maximum value. So this is the solution to the problem. Okay. Now since this maxima and minima are already studied in your higher secondary classes, so we should not waste much time with such discussion. Let us now proceed to the Taylor series and Laurent series expansion as follows. So the Taylor's and Maclaurin series expansion. Taylor's theorem states as follows: let fx be a continuous function of x having derivatives up to nth and higher orders. Then the Taylor series expansion about a point A is given by f of x is equal to f of a plus x minus a f dash a plus x minus a whole square by factorial 2 f double dash a plus x minus a to the power n by now we can continue it, plus on so on, we can continue it, plus on so on, x minus a to the power n by factorial n f nth derivative at a, and plus so on. So this is the Taylor series expansion about the point A. If we solve it like this, if we write it we write here x as a plus x minus a, right? A plus x minus a, then it is remains same, right hand side is same, f a plus x minus a f dash a plus so on up to x minus a to the power n by factorial n f n a plus so on, right? Now if I put my x minus a as h, if I substitute it, then what I am getting? F of a plus h, okay, is equal to, so that means this is my h, likewise this will be my f of a plus h f dash a plus h square by factorial 2 f double dash a so on plus h to the power n by factorial n fn a plus so on. Here h is a small positive number. Next, coming to the Maclaurin's theorem. It is same. It is simply the Taylor series about origin. So that means if we put a is equal to 0 here, right? If we put A is equal to 0 here, then your Taylor series is same as your Maclaurin series, right? So what will happen to the Maclaurin series expansion? Therefore your f of x is f of 0 plus x minus 0 f dash 0 plus x minus 0 square by factorial 2 f double dash 0 plus so on x to the power n by factorial n f nth derivative at 0 plus so on. So this is your Taylor series expansion, right? This is the Taylor series expansion about origin, or it is your Maclaurin series expansion. And you are familiar with this Maclaurin series expansion. If I ask you find the Maclaurin series or the Taylor series expansion about origin of f of x is equal to e to the power x, right? Then it is a familiar expansion. Already you know the series expansion, but how to get it? So f of x is equal to e to the power x implies f of 0 is e to the power 0 is your 1. So I find the first derivative f dash x is my derivative of e to the power x is e to the power x. So this implies my f dash 0 is e to the power 0 is again my 1. Similarly f double dash x is again here e to the power x. So f double dash 0 is e to the power 0 is your 1. So continue. So now your Maclaurin series expansion is given by f of x is equal to 1 plus x square by 1 plus x into means here f of 0 plus x f dash 0 plus x square by factorial 2 f double dash 0 and plus so on, right? So here if I substitute it, f of 0 is 1 and it is x, f dash 0 is 1 plus it is my x square by 2 factorial, it is here 1 and plus this. So it is my 1 plus x square by factorial 2, similarly here x cube by factorial 3 plus so on. If I want to write it in series form, it is summation of x to the power n by factorial n is equal to here 0 to infinity, right? Now one more thing, while I write the infinite series, this is a infinite power series because this is an infinite power series, right? Infinite power series with center at origin. So every power series is followed by a radius of convergence, right? Since it is an infinite series, so the left hand side is what? The left hand side is my e to the power x. Now it is a function. The right hand side is an infinite series. So this equality is ensured in a domain, right? And here the domain is x mod is infinite here, means it is throughout. Now this region here, this is called the radius of convergence here. This is called the radius of convergence, right? Radius of convergence. This is called the radius of convergence, means this equality sign will valid here, right? This is exactly same as e to the power x and throughout, right? Similarly, if I ask you one more example, if I ask fx is equal to 1 by 1 minus x, what is its Maclaurin series expansion? You know it is 1 plus x square plus x cube so on, and here mod x is less than 1, right? Here the radius of convergence is 1, means this series will valid, the center is 0 and this radius is 1. Within this circle of convergence, this series will valid, means here 1 by 1 plus x will be equal to this, right? Here 1 is called the radius of convergence, right? The radius of convergence is again a different aspect. I will tell you later on what is the radius of convergence, right, while I teach you the power series. So, and how did I get it? Now it is because of the Maclaurin series expansion. Similarly, if I ask you what is sin x, already you have remembered this. Sin x is x minus x cube by factorial 3 plus x5 by factorial 5 minus so on so on so on, right? So this is your summation of minus 1 to the power so this is your minus 1 to the power n x to the power 2n plus 1 by factorial 2n plus 1. If I want to write it in series form, it is n is equal to, I may leave it and or I may write it in this way. So now here similarly your x mode is less than your infinite, means it is valid throughout, but it is valid here in this minus 1 less than x less than 1. Okay, so the region of convergence means this left hand side is a function, right hand side is an infinite series. This equality holds subject to a given region of convergence. Okay, so the detailed discussion will be there while we learn the radius of convergence. Now let us discuss some examples for Maclaurin for Taylor series. You are asked to find the Taylor series expansion of log sin x. Okay, so what is your Taylor series expansion? The Taylor series expansion of fx about x is equal to a is f of x is f of a plus x minus a f dash a plus x minus a square by factorial 2 f double dash a so on so on so on. But here it is given a is equal to 2 here, so it is here f of x is f of 2 plus x minus a f dash 2 plus x minus a square by factorial 2 f double dash 2 so on so on so on. So individually let us find what is f of 2, f dash 2, f double dash 2 and so on. So now if you differentiate, right, so it is my fx, f of 2 is this. If I find the derivative of this, log sin x is 1 by sin x, by chain rule derivative of sin is again cos, it is cot x, so f dash 2 is cot 2. Similarly f triple double dash x, f double dash 2 and f triple dash x, so let it be my equation star. Okay, now star follows. Now I substitute all this thing in equation number star. Now equation star follows, right? So these are so on. Star follows. Here f of x is equal to log sin 2 plus x minus 2 f dash x means cot 2 plus x minus 2 square by factorial 2. Here f double dash 2 is here minus cos x square 2 and so on, right? So this is the desired answer. Which is the desired Taylor series expansion. Next, coming to one more example. One more question is, find the Maclaurin series expansion, means Taylor series about origin of the function log 1 plus e to the power x in ascending power of x up to the x to the power 4 terms containing x to the power 4. Okay, so here the finite number of terms as it is asked in the question, right? So let here y is equal to log 1 plus e to the power x, right? So implies y of 0 or f dash 0, right, or f of 0 is my log 2. It is my log 2. Similarly, I am writing y is equal to fx here. So what is my y1 or y dash or my y1, right? Y dash is my, if I differentiate it, okay, the derivative of this log of this is 1 by 1 plus e to the power x into e to the power x, right? So this implies my y1 0 is my half, right? Then what is my y2? I differentiate it, right, by division formula. Second derivative first, 1 plus e to the power x into e to the power x minus first derivative second is e to the power x by second square 1 plus e to the power x whole square. Okay, so this is equal to, if I take common e to the power x, it is 1 plus e to the power x minus e to the power x by 1 plus e to the power x square, right? So I can write it e to the power x into 1 plus e to the power x into 1 by 1 plus e to the power x, right? So I can write it. You see now this is your e1, this is your y1 here, right? This is your y1, so I can write it here. This is y1 into, I can write it again. So this is 1 minus e to the power x by 1 plus e to the power x. This is again my y1. So this is my y1 into 1 minus y1. Okay. For simplicity, I bring this to y1. Okay. Then similarly, I find my y2 0. So what is my y2 0? Already y1 0. I got it 2 here. So this is my y1 0 into 1 minus y1 0. Already I got it 2. So it is 2 into 1 minus 2. Okay. So it is actually a half. So it is my half into 1 minus half. Right. So this will give you 1 by 4. Likewise, I calculate y3 and y4. So if I differentiate it now, right? Differentiate derivative of first into second. So derivative of y1 is y2 minus y1 plus your first into derivative of second plus y1, and the derivative of second is here minus y2. Okay. So that is equal to here y2 minus 2 y1 y2. So that means here y3 0, if you solve it, it will y2 0 minus 2 y1 0 into y2 0. So this will give you 1 by 4 minus 2 into half into 1 by 4. So this is equal to here 0 here. Now the last one is my y4. I need to calculate. What is my y4? So similarly, I differentiate it to get my y4. So this is here y3, and again here the product formula minus 2y3 y1 minus 2 y2 square, and my, so this implies my y4 0 will be my y3 0 minus 2 y3 0 into y1 0 minus 2 y2 0 square. Y3 0 is already here 0 minus 2 into 0 and minus 2 into y2 0 square is 1 by 16, here is 1 by 8. So therefore my Maclaurin series is like this. So hence the Maclaurin series expansion is given by, it is up to x fourth term. Okay, so I am writing up to x fourth term. So I substitute the value here. So this is my log 2, what is y0, and here y0 is log 2 here, then it is half. So it is log 2 plus x into half plus x square by 2 factorial into 1 by 4 plus it is here 0, x cube by 3 factorial into it is here 0 plus x fourth by 4 factorial, and it is minus 1 by 8. If you simplify it, so this will give you log 1 plus e to the power x is log 2 plus half x plus 1 by 8 x square minus 1 by 192 x to the power 4. So this is up to x to the power 4. Okay. If it is not restricted, we will continue it up to infinity. So in this example, you see, right, this example is a little tricky, because if we usually differentiate and find the result instead of bringing back to y1 and y2, then this calculation will lengthy. Okay, so you should see this example carefully. Now for simple cases, usually it is asked to find the finite number of terms in the series expansion to get a result approximate to a sufficient degree of accuracy. As we see here, we are asked to find up to x fourth, right? And we assume that the expansion is valid. Else, if it is not restricted to find up to a certain degree of accuracy, then we have to find the infinite series, right? Once we find the infinite series, this is actually a power series here, power series, right? with the restriction of circle of convergence. Once we write the infinite series, for the convergence analysis we have to mention the circle of convergence and what is the radius, for the circle of convergence, right? This is called the radius of convergence. So I will just give a brief idea here about the power series and radius of convergence, but the detailed discussion will be there in your subsequent semester. So what is a power series? Basically it is an infinite series in the power of a certain variable x. Means if that means I write it a0 plus a1x plus a2x square plus a3x x cube plus so on. Means here you see the series is written in the power of x here. Here this power is x to the power 0, right? Means I can write it. It is summation of an x to the power n, right? N is equal to 0 to infinity. Or I may write it here an x minus 0 to the power n summation n is equal to 0 to infinity. And this series is valid for some x minus 0 mod is less than r. That means this series is valid in a circle of convergence with this is my center, right? This is my center at origin and the radius is r. Means this series will valid, this convergence is ensured within this circle of convergence, right? So this is my circle of convergence with r as the radius of convergence, right? Likewise we have a power series expansion in the power of x minus a. So likewise we have a power series expansion in the power of x minus a. It is a0 plus a1x minus a, a2x minus a. So it is expressed in the power of x minus a, and I can write it summation of an x minus a to the power n with n is equal to 0 to infinity. And the moment I am saying this, there must be a circle of convergence x minus a mod less than r. That means here this series will converge within a circle of radius of center at a and radius r. Here you see, here the center is at origin here, right? Origin here, and here the center is at a here. Right? Now how to find the radius of convergence? To find radius of convergence, right? Suppose we have this is the power series. Suppose this is a power series. Okay, suppose this is a power series. You see, this is n and this is n, right? Then the radius of convergence is r is equal to an by an plus 1 mod, right? Limit n tends to infinity, right? Limit n tends to infinity. This means the radius of convergence must be positive here. And in some book it is also written like this: 1 by r is limit n tends to infinity an plus 1 by an mod, right? So this is the radius of convergence. If I really want to find the radius of convergence of some simple series, then let us consider some examples as follows. Suppose you are asked to find the radius of convergence of such series. So here you see, so here this series is of the form 1 by factorial n x to the power n. This is my an, So what is my an plus 1? So my an plus 1 is 1 by n plus 1 factorial. So now what is my radius of convergence? My r is equal to limit n tends to infinity an by an plus 1 magnitude. So an is 1 by factorial n. Now this is reversely multiplied n plus 1 factorial by 1, right? Modulus limit n tends to infinity. So this is equal to limit n tends to infinity n plus 1 into factorial n by factorial n. This is cancelled. So now as n tends to infinity, it is infinity. So what is r? Therefore radius of convergence is infinite. Means throughout it is convergence. Okay, it is convergence everywhere. But here what is my an? My an is this. But the center is inbuilt here. The center here is 1 here. The center here is 1. Or I can write it here. X minus 0 mod is less than infinity, right? So this is my circle of convergence with infinity as the radius of convergence. In this example, here an is equal to minus 1 to the power n. So this implies an plus 1 is minus 1 to the power n plus 1. Now what is here r? R is equal to limit n tends to infinity minus 1 to the power n plus 1. Here an by an plus 1 modulus. So this is equal to limit n tends to infinity minus 1 to the power n by minus 1 to the power n plus 1 modulus. Okay. So this is equal to limit n tends to infinity minus 1 to the power n by minus 1 to the power n into minus 1 modulus. So this is cancelled. So now it is 1 by minus 1 modulus. Okay. So this is 1. So therefore the radius of convergence here is 1. And the center is inbuilt here. It is 1 is the center. Or I can write it here. X minus 1 mode. X minus 1 mode is less than 1. So this is the circle of convergence here, and this is 1 is the radius of convergence, right? In some complicated cases, suppose you are asked to find the radius of convergence of summation of minus 1 to the power n x to the power 2n by factorial 2n. You see here, this is an, but this power is here 2n, right? So we can see it here, minus 1 to the power n, it is x to the power n whole square by 2n factorial here, right? By 2n factorial here means instead of r, the formula is for r square, right? So here this is my an, since this power is x to the power n, instead of r, the formula is r square is equal to here limit n tends to infinity an by an plus 1 magnitude. Okay. So because this is x to the power n whole square, accordingly we will take the power. So this is equal to limit n tends to infinity minus 1 to the power n by 2n factorial into, this is 2n plus 2 factorial, right, by minus 1 to the power n plus 1. So now this minus 1 to the power n and this, it becomes here positive because we have a modulus sign here. So this is limit n tends to infinity, it is 2n plus 2 into 2n plus 1 into factorial 2n divided by 2n factorial. If I take limit n tends to infinity, it minus 1 to the power n, and it is 1 by minus 1 to the power n into minus 1 modulus. Okay. So now the contribution of modulus is just make it positive, and this cancel. So this is just positive here. Now this is infinity. So therefore the radius of convergence r square is equal to infinity implies r is equal to infinity, and this, since it is x in the power of x, so the center is 0 here. So I can write it here, x minus 0 mode is less than infinity. So this is my circle of convergence. This is my circle of convergence with this infinity as my radius of convergence. Okay. So this is all about the Taylor series expansion and the Maclaurin series expansion with the basic knowledge of power series and radius of convergence. Now to summarize this, okay, so the Taylor series expansion is an infinite series expansion about the given center. Once the center is origin, then the Taylor series is equivalent to the Maclaurin series. The Taylor series at origin is same as the Maclaurin series. Basically, for simplicity, the Taylor series or the Maclaurin series is being asked up to a certain degree of accuracy, right? Otherwise, if it is an infinite series, we should have the knowledge of the radius of convergence, and accordingly we have discussed the formula for radius of convergence. However, the detailed discussion will be there in higher semesters while we learn the power series in the sense of the complex numbers. Okay, now we are discussing here in the sense of the real number. Okay, so now before we conclude, let me to request you that if this lecture is interesting and useful for you, please subscribe to this channel and also like this channel, which will boost my motivation to upload such lectures for your benefits. So thank you all. Have a nice day.